All right, good morning, everybody. We've got an action-packed seminar today on something that is pretty much a contradiction in terms, basic advanced math. And so we're going to try to break down at a very fundamental level what this whole math thing is all about. We'll give a couple minutes for people to filter on in. And once again, if you have any questions throughout the duration of the seminar, this is supposed to be somewhat interactive, so please feel free to enter them into the chat. I've got this extra monitor over here such that I can see and still give my presentation here. So I'm monitoring that. It's finally gotten a bit chilly over here. It's quite nice. Hope everybody's enjoying the Tri-Cities fall weather. Exactly. There was some discussion in my basic stats class, Stat 212, of getting a tea session when we get back to campus going, like once a week on a Wednesday afternoon for fall semesters and early spring semesters of, just having a room with tea in it at like 3 p.m. Some nice loose leaf stuff. All right, but tea later. We're going to talk about today. Yeah, so I'll keep you posted on that one. But what we're going to talk about today is some basic advanced mathematics, right? We want to understand essentially what's going through the minds of mathematicians when they're developing these different mathematical tools, right? Because as engineers, or in my case, as computational scientists, I don't necessarily need to be doing a lot of advanced math, right? I just need to be able to implement the algorithm and understand the algorithm. But the problem with not being able to understand what's going on is, it's you don't know what's going on. You don't know if you're doing it correctly. You're just you're trying to translate from the theoretical realm to the applied realm. Actually building the thing, the program, the bridge, the whatever. And if you don't really understand the language in which the tool is developed in, I'm skeptical that you truly understand your tool and how all the ways it could go wrong or be misused or things like that. So the goal today is to give you a primer, a sort of Rosetta Stone to understand what's going on under the hood of all these different mathematical tools that we've got. So we're going to talk a little bit about why that's important and where this might be useful. Then we're going to talk about the basics, the fundamental axioms on which mathematics is built, which is the logic of sets, and then logical operators connecting sets. And then we can talk about quantifiers and finally get into our different definitions of things, right? Because we have all these different mathematical concepts, like an integral or a derivative or a limit or things like that. Those have definitions that are built up from these sets, these logical operators, and these quantifiers. And so if you can understand fundamentally these three things, these sets, these logical operators, and these quantifiers, you can at least follow along when a mathematician is having a discussion or makes an argument that you should use this method or that method, or you should do this or that for your tool. Specifically, in your case, and I know this is something I've talked to a number of you engineering students about, This comes up a lot when you're given a tool like finite element methods or Hamiltonian mechanics or something like that. Right? So this is a snapshot from the discretization section of the finite element method Wikipedia article. Right? And if you open up a book on finite element methods, you're going to find all sorts of statements being made in there. Right? And the problem boils down to when you're trying to solve the finite element, a problem, a PDE using the finite element method, is you're looking for a U, such, with some stuff going on, right? So you want to find a U, gibberish, with a finite dimensional version, finding a U in V. Well, I'm already giving some of the game away. Gibberish. And then we've got our subset defined here, gibberish. Now, you had a whole course on the finite element method. And you still probably don't understand how it works, because no one has ever bothered to explain any of this gibberish to you. They might flash it on the screen and say, don't worry about it. This is fundamentally what's going on. But you don't understand what any of these things mean. How can you possibly understand what the finite element method is doing? Right? And this is not just limited to the finite element method. Right? Even relatively simple concepts like a mathematical limit in calculus have relatively complicated technical definitions. Right? We have this sort of informal notion of what a limit is, just like you might have an informal understanding of how the finite element method works. But technically, what a limit is gibberish to you. Right? And that's why limits give people more difficulty in Calc 1 than I say derivatives or integrals. Because the informal notion of the limit is a little bit more abstract, a little bit harder to comprehend than the informal definition of a derivative and the informal definition of an integral. Right? Integral, area under the curve. Derivative is a slope. A limit, it's something that we're not really familiar with. Right? So here, this is a technical, there are other definitions, but this is the formalized version of the definition of a limit that was used for the longest time. It's not the only one. This is still the most common one, but this is the formal definition of it. The problem is, even for a concept that you can manipulate relatively well, like a limit, is you still have no idea what's actually happening under the hood. You still cannot evaluate whether or not this definition holds for any given claimed limit. So what we're going to talk about today is how to read this thing. That way you can follow along other mathematicians when they make other claims about, say, the finite element method, or something else, a finite volume method, or some integral calculation. This talk is not designed to essentially make you a mathematician. That takes several years of coursework. So you're not gonna go out here and say, oh, I'm gonna prove the uniqueness and existence of some solution to a partial differential equation. It might make you interested in those kind of problems, so you can take the coursework in grad school or whatever, but it's not designed to get you in the position to do that. You're not gonna be a mathematician after this talk, because we don't have time for that. All right? I'm trying to give you the lay of the land and give you an understanding of what's going on and how to follow along mathematicians when they're making arguments, so that you can sit down and sort of nod your head when the mathematician says, this is why finite element method with this set of basis function works this way. Right? So you can vaguely understand. You're not going to understand all the specifics, because you're not going to understand all the definitions of the concepts unless you go and look them up. But you'll at least be able to say, okay, so we're looking for a function u in the set of functions given by h, such that for all of my v's, also in h, we have some quality satisfied. That's what I'm looking for. I'm looking for a v and a u that satisfies this quantity, and those v's and those u's live in certain sets of functions. They live in a collection of functions that have certain properties. And you can use those properties to prove that this will work. If you didn't have h here, the finite element wouldn't work. So we're going to understand that's what we're after. And the most fundamental thing in order to achieve this is the notion of sets. If it'll let me go to the next slide. We want to talk about sets and the notation of sets and the relationships of sets to each other. Axiomatically, the smallest foundations they've been able to get mathematics to work on is the logic of sets. So this is essentially what mathematics is based on. It's the fundamental building blocks of all of mathematical fields. Right? You did first learn about sets in linear algebra. You must have, because linear algebra is when you first start talking about spaces. Right? And spaces are a certain type of set. Vector spaces. With a certain dimensionality. They're sets of certain properties. So if you're going to understand a vector space, or a null space, or a column space, you need to understand sets at a very basic level. All right? So sets are at their most basic level collections of objects. Right? And those objects can be anything. We like to think about sets of numbers, but it can also be sets of vectors, sets of functions, sets of sets. Sets of, any sort of mathematical object can be placed in a set. And we're just talking about a collection of those objects. All right, so we can talk about the set of all math professors at WSU-TC. And there's a certain amount of objects in that set, a certain amount of things. But that's not really a mathematical concept. That's just a everyday concept. We can also talk about the set of all real numbers. So when we refer to that, we're saying, look, here's a group, a class of things that all share some quality. The quality is that they're real numbers. We can talk about the set of the 20 tallest buildings in North America. And there are 20 things in that set. The Sears Tower, One World Trade Center, all of those things are in that set. So the members of the set, the individual things, are known as elements. And sets can have a finite or an infinite number of elements in them. The set of all math professors at WSU Tri-Cities is relatively small. There are 4 of us. The set of all real numbers is a little bit bigger. There's at least 12 real numbers that I can think of. They've hypothesized up to 15 real numbers in the fields of mathematics. I'm joking, there are infinite many real numbers. All right, so if we have S denoting our set, if we say, here's a set S, we can talk about the membership of that set. And we can use notation to do that. So we have here X is in S. This tells me that whatever X is, a number, a person, a building, it's a member of this set. Similarly, if we put a line through it, just like we can do with the equal sign, when we say X is not in S, that tells us that X is not an element of S. Whatever S is, whatever set is, whatever collection that is, X is not in there. And so we can already start piecing together what these relatively advanced finite element statements are. Find U, the function U, in the set of functions H10 such that we have these qualities. We're looking for a U in a certain set of functions. So let's take a look at the set of all U.S. presidents, something nice and non-mathematical before we really get into the thick of things. All right? So which of the following are true statements? Millard Fillmore is not in S. Barack Obama is in S. Thurgood Marshall is not in S. Is Millard Fillmore not a member of the set S, where S is the set of all U.S. presidents? Well, Millard Fillmore was a president, so he would be in S. So this statement here is incorrect. This is a false statement. On the flip side, Barack Obama, he was a president, so he is in the collection of U.S. presidents, so he is in set S. And additionally, Thurgood Marshall, he was on the Supreme Court. He wasn't a president, so he's not in S. So this statement that he's not in S is in fact true. So we can talk about whether or not something is in a set. But we need to be able to say more than, oh, things are in sets and things aren't in sets. We also need to be able to say what a set is, how to build that set, how to get at that set. And we have a variety of ways of doing that. All right, so we can list out our membership within curly braces, right? So if S is a set of numbers, and here's that set of numbers, we can list out those members. Right, so we've got 1, 2, 3, 4. S here is the set of 1, 2, 3, and 4. We call this set roster notation because a roster is basically just a list of membership. If you have a roster of, Seattle Seahawks players, you have the list of the players that are Seattle Seahawks. Right, but this is limited for a number of reasons, right? Because if I want to talk about the set of all real numbers, well, I have to say, all right, well, let's let the set of all real numbers R be equal to 0. Let's start at 0. That's a good place to start. And then 0.1 or 0.001, or I skip the 10th. I'm going to have a tough go of things, right? There's a lot of numbers I need to list in there. So set roster notation is fine when you have a relatively small finite set, or if you have a set that follows some clear pattern. So you could say S is equal to 2, 4, 6, 8, ... And that one says, all right, I have an infinitely large set, but I can basically figure it out. This is the even numbers, greater than 2. The even natural numbers, if you like. But that requires a nice pattern that we can understand. So instead of using set roster notation, most of the time we use what's called set builder notation, which is down here. All right, and this tells us what our set is in relation to another set. All right, this says the set S is equal. I messed up my notation here. Let me change that to an I. It's equal to the set of natural numbers I, so the set of i's in the natural numbers, where I is less than or equal to 4. So we could use this to build that set up, right? So i's in our natural numbers, so we get 1 is our first natural number. That is less than or equal to 4, so that's in our set. 2 is in natural numbers, and 2 is less than or equal to 4. So we put 2 in there. 3 is in our set of natural numbers, and 3 is less than or equal to 4. 4. 5 is in our set of natural numbers, but it's not less than or equal to 4. And none of the other ones will be. So this gives me a concise description of my set. The set's the same. This set S is the same as that set S. They're the same. It's just we have different ways of describing those. So that's our set. First one, set roster, and this is set builder notation. And we often have sets that we want to build off of, right? We don't want to define every set again and again and again. So we'll use a collection of other sets of numbers or functions or whatever. Right. So what do you mean the related sets? You're asking specifically about this N, I think. Yes, at some point, someone needs to rigorously define and has rigorously defined what constitutes a natural number, what constitutes a whole number, what constitutes an integer, right? And then we build off our sets for our specific purposes off of those. But yes, foundationally, based on a small number of axioms that you just have to assert, right? So yes, the set of real numbers is defined on the basis of another set of things, right? And that's getting into there's a whole subject on that called real analysis. And if we have time today, I will show you the proof that shows that we cannot get real numbers, or we cannot just get off, we just can't suffice on this set of numbers. We have some proofs at the end today where I'll be like, look, we know there are numbers out there that are outside of our sets that we can get intuitive understanding of. So yes, real numbers are defined in the field of real analysis. The first chapters of a real analysis book. There's the guy that wrote the book, Principles of Mathematical Analysis. That is a really good introduction to that. But yes, fundamentally, you need a certain set of axioms, and from those axioms, and their set theory axioms, you can get the rest of mathematics. But no, the real numbers are not just axiomatically defined. They're built upon from a different set. All right, so n is our natural numbers, our counting numbers. 1, 2, 3, 4, 5, all the way up to, infinitely many counting numbers. Okay, good. We also have our whole numbers, which is the natural numbers with the addition of 0. 0, 1, 2, 3, 4, 5, and so on. All right, but then we invented debt, and we said, not only do I have things that I actually have, I have negative things. I have things that I have less of than 0, less than none. So -2, -3, -4, all the way down to negative infinity, -1, 0, and then our natural numbers again. Then we have our rational numbers, which are given by just ratios, rational ratio of integers. So like 1/2, or 3/4, or, whatever, 1/999. Those are our rational numbers. They're ratios of integers. Then we have irrational numbers, which are just the not rational numbers. They're numbers that we cannot get as a ratio of two integers. Then we have real numbers, which is essentially the union, the combined rational and irrational numbers on the real number line. Then we have complex numbers for numbers that aren't real. And then we have prime numbers, which satisfy a certain property. They don't have very many factors. They only have specific factors allowed. Right? So we're not going to talk about the definition of any of these things. Well, I'll show you this one's definition. But we're not really focused on number theory. Number theory is the definitions and the understanding of how we get these different sets of numbers. Right? I just want you to know that when you see an n in this discussion, or you see an r, if you see x in R, that means we're talking about x is a real number, the real number x. If you see x in Q, that means x is a rational number. If you see, k is in Z, that means k is an integer. And Z comes from the German for integer. It's a German. Germans are good at this kind of stuff. Math. So k is in Z. Z is the integer set. So we can describe how sets relate to each other. So if we have a set A here, which is the numbers 1, 2, 3. If we have the set B here, which is the set of natural numbers. If we have the set C here, which should be capitalized, which is the set of x in n, such that x is less than 4, we can talk about how these sets relate to each other. Now, A is 1, 2, and 3, and C is the natural numbers less than 4, which is the numbers 1, 2, and 3. I can say they're the same set. They're equal to each other. So I would say A is equal to C. But sometimes sets aren't equal to each other, right? B is the set of all natural numbers. It's more than just 3 of our natural numbers. So A is not equal to B. But they do share some elements. And I want to come up with a way of describing the fact that they share some elements. And the way I'm going to do that is by saying A is a subset of B. A has some elements of B, but B has more. And all the elements of A are also in B. Because A is the collection 1, 2, and 3. Well, B is the collection, the set of 1, 2, 3, 4, forever. So A is a subset of B. Right? And if it's a possibility that B is equal to A as well, we say it's a subset or it's equal to. So in this notation right here, this horseshoe with a line under it, that says A is either all the elements in A are in B, and B may or may not have more. So it is accurate to say here, A is a subset equal to C. Because all the elements in A are also in C. So you could say that that's a true statement. But you can also say, look, B definitely has some elements that aren't in A. All the elements of A are also in B, but B has more that aren't in A. And so we call this notation here, this is a proper subset. So the statement A is a subset of C is true because they're the same set. But the statement A is a proper subset of C is what? It's false. Because in order to be a proper subset, there needs to be some things in C that aren't in A. So that's what this notation means, right? And we saw in the definition of finite elements, V was taken to be a subset of our H10 space, our set of functions. H is a set of functions, V is a smaller set of functions, or it could be the whole set of functions again. But if it's in V, it's definitely in H. So once we've got our sets defined, we can start thinking about our logical operations on those sets and talking about how they relate to each other using logical connectors so we can build up from there. All right? So another fundamental building block of mathematics is not just sets, but also propositions. So when a mathematician says 1 plus 1 equals 2, he's making a mathematical proposition. You think of that as an equation, but it's a proposition. It's asserting the fact that the glyph 1 with the operator plus another glyph 1 is equal to some other glyph, some other symbol. And every mathematical proposition is either true or false. We might not know whether or not it's true or false yet, but it's either true or it's false. So I want to show you real quick a little digression. This is Bertrand Russell's, a famous logician's, proof of the claim 1 plus 1 is equal to 2. He didn't take that as a fact. He built up a minimal set of axioms, used logical arguments, logical connections, definitions of equal to and stuff. It took him 380 pages of work to get to the claim 1 plus 1 equals 2. And he was being a bit cheeky. He wasn't kind of intentionally making it as difficult as possible because he wanted the smallest set of axioms at the very beginning to start with. And he said, you start with this very, very small set of axioms. You can build up a system of mathematics where 1 plus 1 does equal 2. And he's demonstrated that in 380 pages of work. So these propositions, 1 plus 1 equals 2, is either a true statement or a false statement. So if we just take a generic statement, P, and another generic statement, Q, we can start talking about more complicated logical expressions that relate P and Q. P could be something, a statement about a set, right? P could be the statement, N is a subset of R. And is that mathematical statement true or false? The natural numbers are a subset of the real numbers. This is a true mathematical proposition. But you might have a false mathematical proposition, like Q is a subset of W. That one's false. And so all of these different statements we have, take it 1 plus 1 is equal to 3, that's a false mathematical statement. It's a non-equation. So in regular math you have experience with, this would just be something wrong. If you put that on a paper, you couldn't even put it on a paper without someone saying, "What are you doing that's wrong?" In advanced mathematics, we can talk about this as a statement. We can say, look, this is a statement, but for our definitions of 1, 1, 2, the plus sign, equals, and 3, this is a false statement. And so we're talking about the logic of mathematics at this point. Certain statements are true, certain statements are false. Everything is a statement. So if we have some proposition or statement, same thing, synonyms, P, we can talk about the negation of that with the symbol tilde P. This is read as not P. In some other places you will see this with a little dash that looks like that, not P. Right? And it takes whatever P is claiming and asserts that, P is not the case. So if P is the statement 1 plus 1 is equal to 3, not P would be the statement 1 plus 1 does not equal 3. And one of these statements is going to be true, and the other statement is going to be false. In this case, not P is true, making P false. Each of our statements have what we call a truth value, either true or false. And the truth value of the negation is the opposite of the truth value of the original statement. So in this case, if I know the statement not P, 5.2 is not in the set of natural numbers, if I know that's true, I can make a conclusion about the statement P. 5.2 is in the set of natural numbers. And I know that must be false, because they have opposite truth values. We don't have time to talk about truth tables today, but you can formalize these things. We also have our conjunctive propositions. The conjunction of two propositions is written as P and Q, which is either with the dot or with the sort of caret. It asserts that both the proposition P is true and the proposition Q are true. So this is like the AND operator. So I've got a proposition P here. 2 is in the set of natural numbers. A proposition here that 2 is even. And I have the conjunction of the two. The proposition 2 is in the set of natural numbers and 2 is even. Conjunctive propositions are true only if both of the individual propositions within them are true. So this proposition is true, right? Because both 2 is a natural number and 2 is even are true propositions. But if I had something like 3 is a natural number and 3 is even. This is true. I left off my set of natural numbers. This is true, sure, but 3 is not even, so this is false. So the full conjunction is false. So this takes two propositions and joins them together. And you can stack conjunctions on conjunctions. You can do P and Q and R propositions, arguments. And you can combine these however many times you like. We also have disjunctive propositions. And this asserts that either one or the other or both propositions are true. All right? So this is like an or statement. So here's a disjunctive proposition embedded within some other framework. If x is a natural number, for all the natural numbers x, either x is even or x is odd. And that's true. X is, a number is either, a natural number is either even or it's odd. In this case, it can't be both. But you also might have a disjunctive proposition that's false, like x is even, or, let's use our notation, x is odd, or sorry, is prime. For all x, for all natural numbers x. There's a natural number that is not even. Let's say 9. When x is equal to 9, x is not even, and x is not prime. So this statement is false. The disjunction is true if either one or both of the individual propositions are true. Now to get into the nitty-gritty ones, we have conditional statements. These are the if-thens of the mathematical world. If x is even, then x divided by 2 is a natural number. If P is true, then Q is true. And so we denote our conditional statements with an arrow. P implies Q is how I read this. Right, there is an order of operations to these, whereas if you do not P or Q, that is going to say not P. So you would need to group those together as P or Q, not, if you want to negate the disjunction. And a fun fact of this, there's a logic law called De Morgan's law that says this is equivalent to the statement not P and not Q. If neither P nor Q are true, which is the equivalent of the negation of P, not P or Q, then the statement not P and not Q must be true. So yeah, you need to use your groupings. The order of operations is urinary operators first, so the nots, and then 2, and or, left to right. And then we have our conditional operators. So you apply this first to here, and then you look at this. But yes, good question. I was actually looking for my order of operations slides on these, and I could not find it. I know them, but I didn't want to make the slide again. So I said, if it gets asked, I'll just write it out on the side. All right, so we could say x is even implies that x divided by 2 is a natural number. That's not true. It's not a natural number, it's an integer. But we could say that. This statement is false. This statement is now true. We could say A is equal to 0 implies A times B equals 0. Is that true? If A is equal to 0, will A times B equal 0 for any natural number B or any real number B? Yes. All right, but let's look at the reverse. A times B equals 0 implies A is equal to 0. Is that necessarily true? If I know A times B equals 0, let me write that down actually. Exactly, it could be B. B could be the 0, 1. Conditionals go one way. That's what the arrow means. One gets you to the other. You can't go in reverse. That's called a logical fallacy, which is called affirming the consequent, or the converse error. A, B equals 0 does not imply A equals 0. But sometimes the conditionals do go both directions, and we call those biconditionals. Sometimes both P implies Q and Q implies P, and that gives us a biconditional. So we draw the arrow going both ways, and we say P if and only if Q, which is the same as saying Q if and only if P. So X is even if or only if and only if X divided by 2 is a natural number. A times B equals 0 if and only if A is equal to 0 or B is equal to 0. Right, we've got our disjunction there. And this has a name. This is a true statement. Does anyone know what this is called? This is our zero product property. And that's what lets us solve basically all of our polynomial equations. If I give you x minus 3 times x is equal to 4, you can't solve that. But if you move the 4 over, well, let's x minus 3 x is minus 4 is equal to 0, you can start solving that. Right? You're going to have to refactor it such that you get your actual factors. But if I get x minus 3 times x is equal to 0, can I solve that? Yeah, either x is equal to 0 or x is equal to positive 3. This is what lets you solve your polynomial equations, the zero product property. You get everything on one side, factor it, and you know that this will be equal to 0 if and only if one or more of its factors is equal to 0. All of the definitions you work with are biconditional statements. If you know the definition is true of some number, then you know the thing is of some concept. So if I know a number x divided by 2 is an integer, then I know that number is even. If I know a number is even, I know that x divided by 2 is an integer. All right, so let's use some set roster or set builder notation and some of our logical operations to practice these compound statements, define some larger things. So let's talk about the set of x's such that x is a member of A or x is a member of B. X is in A or x is in B. What's the set of x's that gives me that? What x's make this statement true? Well, 2 is in both, so it's definitely in A or in B. 3 is in this one. 3 is in A. And we only need one of these to be true for the statement to be true. So 3's in there. Same with 5 and 7. 4 is in B, which making this part true, making the whole thing true. So 4 is in there. 6 is in there. This defines a specific concept for two sets. Does anyone have a guess what that is? I ask all of my statistics students who should know what it is. This is our union of sets, A union B. It's the union. Yes, well done. All right, now see if you can't go from there. The set of elements that are in both A and in B. What's that set? Well, it needs to, both of these things need to be true. It's only 2, exactly. This is not our union. This is A intersect B. And we can talk about the overlap of our sets. The only overlap between these two, the only shared element of them is A is 2. 2 is both in A and B. The last thing I want to talk about are some quantifiers, right? The last piece of our puzzle. And those quantifiers let us talk about either all the membership of a certain set, or if there exists some overlap, or there's no overlap. So we use quantifiers for these purposes. So if I want to make a claim about all the membership of some set, we use this upside down A quantifier. And that is, we read that as for all. When you see that, read for all. So I read this for all x in the set of real numbers, x times 0 is equal to 0. For all x's and y's in the set of real numbers, y not equal to 0 implies that x divided by y is a member of R. X divided by y is a real number. So we use this to talk about all the membership of some group. And then we can build a conditional off of those two. Right? This is a true statement, right? If y is not equal to 0, x divided by y is a real number. This is a true statement. It doesn't matter what x is in R. X times 0 is going to be equal to 0. So we're talking about all of some group. We can also talk about that there exists at least one thing in a group. There exists at least one element that satisfies a certain property. There exists an x in the set of real numbers such that 2 times x is equal to 4. So this backwards e here is the existential quantifier. There exists. So the statement A is even is true if and only if there exists some k in the set of integers such that A is equal to 2 times k. This is the formal definition of even. If I know there's some integer k, say 2, such that 2 times 2 equals a, if a is equal to 4, then I know that 4 is even. On the flip side, if I know that n is an even number, I can say, based on the definition of even, that there is some number, I don't know what it is, there is some number k such that n is equal to 2 times k. And so whenever I see n in my equation, I can substitute 2k, and I know it's the same thing because I know n is even. And the even means the same thing as this. The definition of odd is A is, or let's use B, or not. B is odd if and only if there exists some k in Z such that B is equal to 2k plus 1. And that's your formal definition of an odd number. So we have existential quantifiers and universal quantifiers. The upside down A and the backwards E. Now we can stack these on top of each other and get what are called universal existential statements and existential universal statements. Universal existential, existential universal. A universal existential statement is the claim that for all the membership in some class, there exists a corresponding y for that x in another group, such that x plus y equals 0. So here we've got, for all x in the set of integers, there exists the y in the set of integers, such that x plus y equals 0. What is this statement telling us about? You might have seen this statement before in another way as well. This is the additive inverse property. No matter what x I pick, there's a corresponding y, which is different for every x, every different x, that causes this to be the case. So there exists for every x in Z, there exists a corresponding y, subject to some property. So this is your additive inverse property. But we also have existential universal statements, which claims that there exists an x in R that applies to all of y in R. There is a single x, one x for all of y, such that x times y is equal to x. Does there exist an x in the set of real numbers such that no matter what real number you multiply it by, that specific x is what you get out in the end? Yeah. This is a true statement because x is equal to 0 makes this true. Doesn't matter what y is. For all y's, this specific x works. So that's the difference between our universal existential and our existential universal. Right? If you want to think about this one in sort of layman's language is, for everybody in the world, there is somebody. Infinity is not a real number. Infinity is what we call in the extended reals, right? So the extended reals are, let me see, are negative infinity, all the real numbers, and positive infinity. And those are our extended reals. So this one is the statement that for everybody, there's somebody that loves them, right? Their mom, their dad, whoever, their wife, spouse. For everybody, but it's not the same person for everyone, right? This is saying everybody has a corresponding person who loves them, right? And it's different for every different person. On the flip side, this one is saying there exists somebody who loves everybody, like Mr. Rogers or Santa Claus or Jesus. So this is specific x, specific y. This is a specific x for every y. So finally, we have the tools to understand these different definitions that are being thrown our direction. X is even if and only if there exists an integer k such that x is equal to 2 times that integer. A divides b, or b is divisible by a, if and only if there exists an integer k such that b is equal to k times a. If that integer does not exist, a does not divide b, b is not divisible by a. A number, r, is in the set of rationals. R is a rational number if and only if, for all a and b that are integers, a divided by b is equal to r, and b is not equal to 0. And then we have our formal definition of prime. X is a prime number if and only if x is greater than 1, and x and r are in the set of natural numbers such that r is equal to f implies either r is 1 and s is x, or r is x and s is 1. And I don't want to dwell on that because that's complicated. But you can see how complicated we can build things up with this. And now we finally have the tool to understand the definition of a limit, if we wanted to. We can read this now. So the limit as x approaches c of the function f of x is equal to L if and only if, for all epsilon greater than or equal to 0, there exists a delta greater than or equal to 0, such that for all of x in the domain, there 0 is less than, go away, 0 less than x minus c, the absolute value of that less than delta, implies, so if this is true, then this is true. Basically, no matter what positive epsilon we pick, there's going to be a delta that will get us to within epsilon of that limit function. So I don't expect you to know necessarily all of this right now, but the point is you have the tools that you can understand each bit in a vacuum and then understand the full thing together on the basis of that. And then you can operate with a foundational understanding of what a limit actually is and means, because you understand what all these symbols mean. And you can start getting at this description of finite element methods, right? We're looking for a u in this set of functions such that for all v in that same set of functions, this operation is equal to the integral of f times v. Now all you need to do is define what this operation is and define what this space is, this set of functions. This is the inner product, it turns out, and this is a Hilbert space. But you need to take some functional analysis if you really want to answer that. All right? Then we built some subset here. The set of v such that on the interval 0 to 1 in R, such that v is continuous, blah, 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 blah. And you can start to piece together what's going on in these circumstances. You can follow along, you can nod along when those mathematicians are talking about why you should use this method and how it was defined. All right, so I'll take any questions now. But if we finish that, we'll work through how we can use these definitions and notations to prove some relatively interesting results. We might have to do a whole separate seminar on relations and the methods of proof in mathematics. All right, well, if you have a question, please type it in the chat. What I'm going to do now is essentially sketch out this proof. And this works for any digit number, but I just use 3 for convenience. If n is a 3-digit number, a 3-digit natural number, with the digits d1, d10, d100, then if 3 divides the sum of those digits, then 3 divides that number itself. All right, so the number might be 366. which means D1 is 6. D10 is 66, or is 60. Well, D10 is 6. And D100 is 3. And my claim is, if D1 plus D2, or sorry, D10, plus D100 is divisible by 3, then 3 is a factor of 366. And I don't want to just prove this for 366. We don't want to do what's called proof by example, where we show it works for a certain number of cases. We want to show it works for all cases. So what we're going to do is we're going to take some n and its decimal expansion, which is what this is called. Right? So I'm going to take the claim n is equal to D1 plus 10 times D10 plus 10, or 100, times D100. Right? And that's true, right? That's just the decimal expansion of this number. What I can now do is something interesting. I can factor my 10, well, not even factor yet. I can use substitutions for 10 and 100. And I can substitute 9 plus 1 for 10 and 99 plus 1 for 100. And I get n is equal to D1 plus 9 plus 1 times D10 plus 99 plus 1 times D100. Then I can use my distributive property to distribute each of these. And I get n is equal to D1 plus 9 times D10 plus D10, using my distributive property, plus 99 times D100 plus D100. Now, using my commutative property of addition, I can rearrange this to get n is equal to 9 D10 plus 99 D100 plus D1 plus D10 plus D100. Now, I can factor a 3 out of this, right? I can use my associative property and the distributive property together. I'm going to jump up here now because I'm out of space. To say n is equal to 3 times 3 D10 plus 33 D100 plus D1 plus D2 or D10 plus D100. Now, using this statement here, which I can assume because it's the if part of the if then, I can go back to the definition of divides. And I can say, if and only if 3 divides D1 plus D10 plus D100, I can rewrite that using the definition of divides as 3 times some integer. This is not an equal. This implies there exists some integer k such that D1 plus D10 plus D100 is equal to 3 times K. So when I see this in my equation, what can I substitute it with? My equation for N. I can substitute D1 plus D10 plus D100 for 3K if 3 divides D1, D10, D100. So I can take this and just substitute 3K in there because I have an existential statement based on the definition of divides. What can I now do to this expression? I can factor 3 out of this and out of that. Which gives me 3 times 3 D10 plus 33 D100 plus K is equal to N. Now this is just an integer. This is just an integer. This is just an integer. Which means this thing in here, through a property we call closure, is going to be an integer. So there is some integer j such that n is equal to 3j. So what can I say about n at that point? If n is 3 times some integer, n is divisible by 3. 3 divides n. Right, n is also an integer. But more fundamentally, this is the definition. 3j, where j is an integer, is equal to n, is the definition of divisible by 3. So we have proven that if you've got this, for whatever number, then you can get to this. And so if you have any number, 149, if the sum of its digits, 1 plus 4 plus 9, is equal to 3, then it's divisible by 3. 1 plus 4 plus 9 is 14, which is not divisible by 3. So 3 does not go into 149. All right, but 150, 1 plus 5 plus 0 is equal to 6. 3 goes into 6. 3 goes into 150. We've sketched out, this is the proof, essentially. You want to document each of these steps of the justification, like associative property or substitution, distributive. But that's the proof right there. And it's all of this, all of the mathematics that you're ever going to encounter is built off of definitions and the mathematical logic that we covered today. So any more questions? Well, that is it for today. I'll stick around for a little bit if you've got any questions. If it's just taking a while. I'll stick around for another 3 minutes. You can also use the definition of rational number. Good. So if you can use what's called an indirect proof, or a proof by contradiction. Let's say we assume the square root of 2 is a rational number, so we can use the definition of rational number to say, well, then if square root of 2 is a rational number, then there's an a and a b, where a and b are integers, and b is not equal to 0. You can further assume that a and b is the simplest form of the square root of 2 as a rational number. So they share no factors. All right, well, you square both sides and you get 2 is equal to a squared over b squared. And so you get 2b squared is equal to a squared. Which means that a squared is an even number, right? Because a squared can be represented by 2 times some integer. And if a squared is even, then a is even, it turns out. So a is even here. We've just established that. You can also show through this by substituting in the definition of an even number for a. If a squared is even, then we can write that as 2 times some integer k. Or if a is even, we can write that as 2 times some integer k. So we've got 2 times some integer k squared for a squared. So you get 2b squared is equal to 4k squared. Divide both sides by 2. You get b squared is equal to 2k squared. K is some integer, making this some integer, making b squared even, which means b is even. But in building this, we assumed a and b had no common factors. If a is even and b are even, b is even, what do we have? A and b both have a common factor of 2, despite the fact we set out as a rule that they could not. We chose them such that they didn't. We've arrived at a contradiction. Right? And if you show that your assumptions lead to a contradiction, your assumptions must be wrong. And our assumption that is wrong here is that the square root of 2 is a rational number. There is no integer a and integer b that will give us the square root of 2. Just by using the definitions of even and rational numbers, you can show that there's something else out there. Which brings you to the need for real analysis and the definition of real numbers. All right, so that's it for today. Hope everybody enjoyed. But yeah, I think we'll want to go ahead and reschedule. I don't think I can do one in 2 weeks. Well, I'll just get in touch with you on that one. I've got a very busy 2 weeks coming up, so I'll just be in touch. But yeah, everybody take care. Enjoy the nice cool weather, and I'll see you for the next seminar whenever we schedule that. How do I stop this? There we go.